Hello, and welcome to Sleepy Science by Nem Vita. Whether you're listening at the end of a long day or simply letting your thoughts slow down, this is a place where curiosity unfolds gently. There's nothing you need to solve, nothing you need to remember, and nothing you need to focus on. If you find your attention drifting, that's perfectly fine. Let the words become a soft background, and let your body settle into rest. Allow your breathing to soften, slow down, and become quiet, steady, and easy. I'm glad you're here. Mars formed in darkness, in the quiet cold of the early solar system, where dust and rock drifted slowly through emptiness. There was no sound, no light yet, only particles moving in patterns governed by forces too slow and too vast to notice. Over time, these particles found one another. They collided gently, stuck together, built something larger grain by grain. What began as nothing more than scattered fragments gradually became a world. This process took millions of years, perhaps tens of millions, a span of time so long that it loses meaning in ordinary terms. There was no urgency, no moment when Mars suddenly appeared. Instead, it assembled itself patiently, drawing material from the disk of debris that surrounded the young sun. Gravity pulled these pieces inward, and with each addition, Mars grew a little more solid, a little more real. Earth was forming nearby, undergoing the same slow accumulation. Both planets began as clouds of dust and rock. Both gathered mass from the same ancient material. Both emerged from the same cosmic process. But Mars, positioned farther from the Sun, had less material to work with. The region of space where it formed was thinner, quieter, and so Mars grew smaller. It reached perhaps half the diameter of Earth, and only about a tenth of Earth's mass. This difference, small at first glance, would shape everything that followed. Size matters in ways that are not immediately obvious. A smaller planet cools more quickly, the way a small stone left in the sun loses its warmth faster than a large boulder. Inside Mars, heat from the planet's formation and from the decay of radioactive elements kept the interior molten for a time. This heat allowed Mars to differentiate, meaning the heavy metals sank toward the center while lighter rock floated to the surface. A core formed, dense and metallic, surrounded by a mantle of semi-molten rock. For a while, this core generated a magnetic field, a protective bubble that wrapped around the young planet and shielded it from the solar wind. The solar wind is a stream of charged particles constantly flowing outward from the sun, invisible but powerful, capable of stripping away atmospheric gases if nothing blocks its path. Mars's magnetic field, in those early days, provided that protection, deflecting the solar wind around the planet, like water flowing around a stone in a stream. But the heat did not last. Mars, being small, could not hold on to its internal warmth as Earth did. Over hundreds of millions of years, the core began to cool. The churning motions that had created the magnetic field slowed and eventually stopped. The field weakened, flickered, and finally vanished. This was not a sudden event, but a gradual fading, imperceptible on human timescales, but inevitable on planetary ones. Without the magnetic field, Mars became more vulnerable, more exposed to the forces streaming from the sun. The distance from the sun also played its part. Mars orbits farther out than Earth, receiving less sunlight, less warmth. The sun in Mars's sky appears smaller, its light a little dimmer. This meant that even when Mars was young and more active, it was always a cooler world than Earth. The energy available to drive weather, to move air and water, was more limited. Everything happened more slowly, more gently. The young Mars had volcanoes, though not as many or as active as those on Earth. These volcanoes released gases from deep within the planet, gases that rose into the sky and began to form an atmosphere. Carbon dioxide came first, along with water vapor, nitrogen, and traces of other compounds. These gases accumulated slowly, building up over millions of years, creating a blanket of air around the planet. This atmosphere was different from the one Mars has now. It was thicker, denser, capable of holding in some of the sun's warmth. The pressure at the surface was higher, enough to allow water to exist in liquid form under the right conditions. The greenhouse effect, caused mainly by carbon dioxide and water vapor, trapped heat that would otherwise have radiated back into space. This made Mars warmer than it would have been with no atmosphere at all. The volcanoes themselves were impressive features, though they grew slowly, building up layer by layer over immense periods. Olympus Mons, the largest volcano in the solar system, began to form during this time. It would eventually rise nearly 25 kilometers above the surrounding plains, a mountain so vast that its base would span an area roughly the size of France. But it did not grow quickly. Each eruption added only a thin layer of lava, and millions of years passed between major episodes of activity. The mountain rose quietly, without drama, accumulating height the way sediment accumulates at the bottom of a lake. Other volcanoes dotted the surface, particularly in a region called Tharsis, a vast bulge on one side of the planet where the crust grew thick and volcanic activity concentrated. These volcanoes poured out lava and released gases, contributing to the atmosphere, changing the surface chemistry, reshaping the landscape in slow motion. The lava flowed like thick syrup, creeping across the ground, cooling and hardening into rock that would remain largely unchanged for billions of years. The gravity on Mars, weaker than Earth's, meant that volcanic plumes could rise higher into the atmosphere, and lava flows could spread farther before cooling. Mountains could grow taller without collapsing under their own weight. The landscape took on shapes that would be impossible on a larger planet, features stretched and exaggerated by the lower gravity. As the planet cooled and the volcanic activity began to decline, the rate at which gases were released into the atmosphere slowed. Fewer eruptions meant fewer gases being added to the air. At the same time, the atmosphere itself was changing, losing molecules to space, being altered by sunlight and chemical reactions. The balance between what was being added and what was being lost started to shift. Mars has a day that is almost the same length as Earth's, just a little over 24 hours. This rotation helped distribute heat around the planet, though not as effectively as on Earth, where oceans move warmth from the equator toward the poles. Mars, with its thinner atmosphere and limited water, experienced greater temperature swings between day and night, between equator and poles. The surface could grow very cold once the sun set, and ice began to form, particularly at higher latitudes. The planet's orbit is more elliptical than Earth's, meaning the distance from the Sun changes more noticeably over the course of a Martian year. This creates more pronounced seasonal variations, with some periods receiving significantly more sunlight than others. These seasons are long, lasting months because a Martian year is nearly twice as long as an Earth year. The slow progression of seasons meant that changes in temperature and atmospheric conditions unfolded gradually, giving the landscape time to respond. During the formation period, Mars was bombarded by meteorites and asteroids, remnants of the same debris field from which it had formed. These impacts cratered the surface, creating bowl-shaped depressions that ranged from tiny pits to massive basins hundreds of kilometers across. The southern highlands, in particular, bear the scars of this bombardment, their surfaces ancient and heavily cratered, speaking to an era of violent collisions. One of the largest impacts created the Hellas Basin, a depression so deep that it drops more than 7 kilometers below the surrounding terrain. The force required to create such a feature was immense, the result of a collision with an asteroid or comet many kilometers in diameter. The impact would have sent shock waves through the planet, ejected enormous amounts of material into the air, and perhaps even contributed to the atmosphere temporarily through vaporized rock and ice. The northern hemisphere of Mars is smoother, lower in elevation, and has fewer large craters. This suggests that something resurfaced this region after the period of heavy bombardment, perhaps lava flows, or, as some scientists propose, ancient seas that deposited sediments over the cratered terrain. The contrast between the rough southern highlands and the smooth northern plains is one of the most striking features of Mars's topography, a division that speaks to different geological processes shaping different parts of the planet. As Mars took its final shape, it became a world of contrasts. Massive volcanoes rose on one side, while deep impact basins scarred the other. The atmosphere, though thicker than it would later become, was still thin compared to Earth's, and the surface remained cold and harsh. Yet within this coldness, within this harshness, there was potential. The presence of an atmosphere, the release of volcanic gases, the warmth from the sun, all combine to create conditions that might, under the right circumstances, allow water to flow. The story of Mars's formation is a story of gradual assembly, of heat and cooling, of volcanoes building mountains and impacts carving basins. It is a story that unfolded over hundreds of millions of years, without witnesses, without record except in the rocks themselves. The planet that emerged from this process was smaller than Earth, colder, more distant from the sun. But it was a world nonetheless, complete with an atmosphere, geological activity, and the possibility of change. This early Mars, still cooling, still adjusting to its place in the solar system, stood at the edge of transformation. The conditions were present for water to appear on the surface, for rivers to carve valleys, for lakes to fill and empty. The planet was poised between its fiery birth and the cold stillness that would eventually define it, holding within itself the capacity for both activity and silence. Water appeared on Mars slowly, emerging from beneath the surface and falling from the sky in cycles that repeated over thousands of years. This was not a sudden flood or a dramatic transformation, but a gradual accumulation. a gathering of moisture that took time to become visible, to leave its mark on the landscape. The water came from several sources. Some of it was locked in minerals deep underground, released when volcanic heat broke chemical bonds and freed the molecules. Some rose as vapor from volcanic vents, joining the atmosphere and eventually condensing into droplets. Some may have arrived from space, delivered by comets and asteroids that impacted the surface and melted upon collision, their ice becoming part of the planet's water budget. The atmosphere, thicker than it is now, played a crucial role. It created enough pressure at the surface to allow water to exist in liquid form, at least temporarily, at least in certain places. The greenhouse gases, primarily carbon dioxide and water vapor, trapped enough heat to raise temperatures above freezing in some regions, particularly during warmer seasons or in lower-lying areas where the air was denser. When conditions aligned properly, when the temperature rose just enough and the atmospheric pressure held steady, water could flow. It began as ice melting on hillsides, as snow turning to liquid during brief warm periods, as groundwater seeping up through cracks in the rock. The water found paths downhill, following gravity, collecting in channels that grew deeper with each flow. These early rivers were not like the great rivers of Earth, wide and powerful, moving vast quantities of water across continents. They were smaller, quieter, carrying less volume, flowing more slowly. But they were persistent. Over time, over countless cycles of flowing and stopping, they carved valleys into the Martian surface, creating networks that branched and merged in patterns recognizable even billions of years later. The valleys tell their own story. They have tributaries, smaller channels that feed into larger ones, the way streams feed into rivers. They have curves and meanders, evidence of water finding the easiest path through varying terrain. They widen gradually from source to mouth, as rivers do when they gather more water along their course. These features could not have been created by anything other than flowing liquid, sustained over long periods. Some of the largest valley networks are found in the southern highlands, ancient terrain that dates back to Mars's earliest days. The valleys cut through cratered landscapes, their channels visible from orbit as dark lines etched into brighter surrounding rock. They are old, worn smooth by time and dust, but their shapes remain clear enough to trace their paths across hundreds of kilometers. Water that flowed through these valleys eventually reached lower ground, pooling in depressions, forming lakes. These lakes varied in size and depth. Some were small, isolated pockets fed by a single valley, filling during wet periods and drying during droughts. Others were larger, spanning tens or hundreds of kilometers, deep enough to stratify into layers, warm at the surface and colder below. The lakes accumulated sediment slowly. Dust and fine particles suspended in the water settled to the bottom, building up layer by layer, each layer representing a period of time when the lake held water. During dry periods, the lakes shrank or disappeared entirely, and the exposed sediment hardened, sometimes cracking into patterns as it dried. Then, when water returned, new sediment was deposited on top of the old, creating distinct layers that can still be seen today in certain formations. Gale Crater, where the Curiosity rover landed, contains such layered sediments. The mountain at the crater's center, called Mount Sharp, is made largely of these layers, hundreds of them stacked atop one another, each one a page in the record of ancient Martian water. The rover has climbed slowly up the lower slopes of this mountain, examining the layers, analyzing their composition, finding minerals that only form in the presence of water. Some of these minerals are clays, formed when water reacts with volcanic rock over long periods. Clays preserve chemical evidence of the water that created them, locking away information about temperature, acidity, and duration of exposure. Other minerals include sulfates, which form when water evaporates and concentrates dissolved salts, leaving behind deposits that crystallize and harden. These minerals speak of changing conditions, of lakes that filled and emptied, of water that was sometimes fresh and sometimes briny. The presence of these minerals across different regions of Mars suggests that liquid water was not confined to a single area or a single period. It appeared in many places, at different times, under varying conditions. Some locations had standing water for long stretches, perhaps thousands or even millions of years continuously. Others had water only intermittently, during brief warm spells or seasonal melts. There is also evidence for what might have been a larger body of water in the northern lowlands. The topography of Mars's northern hemisphere sits several kilometers lower than the southern highlands, forming a natural basin. If enough water accumulated, this basin could have filled to create a shallow ocean, covering perhaps a third of the planet's surface. The shoreline of this hypothetical ocean is debated. Some features that look like ancient coastlines have been identified, terraces and ridges that run roughly parallel to one another at consistent elevations, the way shorelines do. But wind and dust have obscured much of the evidence, and other processes could have created similar features. The question remains open, neither proven nor disproven, a possibility supported by some evidence but not yet confirmed. If such an ocean existed, it would have been shallow, perhaps only a few hundred meters deep at its deepest point. The water would have been cold, near freezing, possibly covered with ice for much of the year. It would not have been a dynamic, wave-tossed sea like Earth's oceans, but a quieter body of water, less energetic, slower to move. Still, its presence would have profoundly altered Mars's climate, providing a reservoir of water that could evaporate and fall as precipitation, creating weather patterns, driving cycles of ice formation and melting. Rain may have fallen on Mars during this wetter period, though probably not as frequently or as heavily as on Earth. The thin atmosphere could hold less moisture, and the colder temperatures meant that precipitation often came as snow rather than rain. But when rain did fall, it would have run across the surface, filling the valleys, feeding the lakes, contributing to the slow but steady erosion of the landscape. Snow accumulated at higher elevations and at the poles, building up into glaciers in some locations. These glaciers, if they existed, would have moved slowly under their own weight, flowing downhill, carving U-shaped valleys, leaving behind deposits of rock and sediment when they melted. Some features on Mars resemble glacial formations, though they are heavily degraded and difficult to interpret with certainty. The climate during this wetter phase was still harsh by Earth standards. average temperatures likely hovered around or below freezing, with only brief periods or specific locations warm enough for liquid water to persist at the surface. The atmosphere, though thicker than today's, was still thin compared to Earth's, providing less insulation, less protection from the cold of space. The sun, smaller and dimmer in Mars's sky, offered less warmth, and nights were long and cold. Yet within these constraints, Mars hosted a hydrological cycle, a movement of water between surface and atmosphere, ice and liquid, that resembled in simplified form what happens on Earth. Water evaporated from lakes and perhaps from the ocean, rose into the atmosphere, condensed into clouds, and fell back to the surface as snow or rain. This cycle, driven by solar energy and mediated by atmospheric processes, allowed water to shape the landscape in lasting ways. The period of warmth and wetness did not last indefinitely. Changes were already underway, processes that would gradually drain the water away, thin the atmosphere, cool the surface. But for a time, measured in hundreds of millions of years, Mars was a place where water flowed and pooled, where rivers carved valleys and lakes accumulated sediment, where the surface was not static but changing, responding to the presence of liquid water. This version of Mars, wetter and more active, existed primarily in the planet's early history, roughly 3.5 to 4 billion years ago. Evidence for it comes from the age of the rocks that preserve water-related features, dated using crater counts and radiometric methods. The oldest terrains, the ones most heavily cratered, show the most extensive valley networks and the clearest signs of standing water. As time passed, these features became less common. Younger surfaces show fewer valleys, less evidence of flowing water, more signs of ice and wind-driven processes. The transition was gradual, spread out over hundreds of millions of years. A slow shift from wet to dry, from warmer to colder, from active to still. But the evidence of that wetter past remains, written into the geology, visible from orbit, measurable by rovers on the ground. The valleys are there, the lake beds are there, the sediments and minerals are there. They tell us that Mars was once different, that it had water on its surface, that it was, for a time, a more dynamic world. Understanding this past helps us see Mars not as it is now, frozen and dry, but as it was, when water moved across its surface, when the atmosphere was thicker, when the planet had not yet settled into the cold silence that now defines it. This knowledge reshapes our view of Mars, transforming it from a dead world into one that has lived through different states, that has changed over deep time, that holds within its rocks the memory of ancient rivers and lakes. The water that once flowed on Mars is still there, most of it, locked away in ice beneath the surface or frozen in the polar caps. The valleys remain, empty now but clear in their purpose. The lake beds sit dry, their sediments layered and preserved. The planet has moved on from that wetter phase, but the traces of it persist. Quiet reminders of a time when Mars was different, when the conditions allowed for something closer to life, to change, to movement. The atmosphere that had allowed water to flow on Mars did not disappear all at once. It thinned gradually, molecule by molecule, over hundreds of millions of years, a loss so slow that no observer could have noticed it happening in real time. But the cumulative effect was profound, transforming Mars from a world where water could exist on the surface into one where the air became too thin, the pressure too low, the conditions too harsh for liquid water to survive. The loss began with the magnetic field, or rather, with its absence. As Mars's interior cooled and the churning motions in the core slowed to a stop, the magnetic field that had once wrapped around the planet faded away. This field had served as a shield, deflecting the solar wind, the constant stream of charged particles flowing outward from the sun. Without it, Mars became exposed, vulnerable to forces that Earth's magnetic field still blocks today. The solar wind is not gentle. It consists of electrons and protons moving at high speeds, carrying energy, exerting pressure on anything in its path. When these particles encounter an atmosphere without magnetic protection, they interact directly with the gas molecules, transferring energy, knocking atoms and molecules loose, sending them drifting away into space. This process, called atmospheric sputtering, happened continuously on Mars once the magnetic field was gone. The upper atmosphere bore the brunt of this loss. High above the surface, where the air is thin and individual molecules are more widely spaced, the solar wind could penetrate deeply, colliding with oxygen, nitrogen, and carbon dioxide molecules, imparting enough energy to overcome Mars's gravity. These molecules, lighter than those on Earth and held less tightly by Mars's weaker gravity, escaped more easily. One by one, they drifted away, joining the flow of particles streaming outward from the sun. The rate of loss varied depending on solar activity. During periods when the sun was more active, producing stronger solar wind and more frequent solar storms, the rate of atmospheric escape increased. During quieter periods, the loss slowed but never stopped entirely. Over time, over immense stretches of time, the cumulative effect stripped away much of the atmosphere that Mars had built up through volcanic outgassing. Ultraviolet radiation from the sun also played a role. High-energy photons struck water vapor molecules in the upper atmosphere, breaking them apart into hydrogen and oxygen. The hydrogen, being the lightest element, escaped into space almost immediately, unable to be held by Mars's gravity. The oxygen, heavier and more easily retained, could still be lost through interactions with the solar wind or by bonding with surface rocks, becoming incorporated into iron oxide and other minerals. This process, called photodissociation, drained water from the atmosphere in a way that was essentially irreversible. Once the hydrogen escaped, the water molecule could not be reassembled. The water was gone, lost to space, never to return. Over hundreds of millions of years, this mechanism removed vast amounts of water from Mars, water that might otherwise have remained in the atmosphere or on the surface. The atmosphere thinned, and as it thinned, its ability to trap heat diminished. The greenhouse effect weakened. Carbon dioxide, the primary greenhouse gas on Mars, became less abundant in the air, reducing the amount of solar heat that could be retained. Temperatures dropped, first gradually, then more noticeably, as the feedback effects took hold. As the surface cooled, more water froze. Ice formed in the soil, in the polar regions, in the shadowed areas where sunlight rarely reached. This ice was no longer available to participate in the hydrological cycle. It could not evaporate, could not fall as rain, could not flow in rivers. It became locked away, buried beneath layers of dust and rock, removed from the active processes that had once shaped the surface. The rivers stopped flowing, not all at once but gradually, as the water that fed them disappeared. Some dried up entirely, their channels becoming empty trenches in the landscape. Others flowed intermittently, carrying water only during brief warm periods or when underground ice melted temporarily before freezing again. Eventually, even these intermittent flows ceased, and the valleys fell silent. The lakes began to evaporate and freeze. Their surfaces turned to ice, and the ice thickened as temperatures continued to drop. Some lakes may have persisted for a time beneath ice covers, protected from direct evaporation, but cut off from replenishment as the rivers that fed them dried up. Eventually, they too vanished, leaving behind only their beds, flat expanses of layered sediment now dry and exposed to the wind. The wind became more important as water became less so. With the atmosphere thinning, wind speeds could increase, particularly during seasonal changes when temperature differences between regions drove air movement. Dust, fine particles of rock and mineral weathered from the surface, began to be picked up and transported across the planet. This dust accumulated in some places and was stripped away from others, slowly reshaping the landscape in ways that water once had. Dust storms on Mars can be enormous, sometimes encircling the entire planet, lifting dust kilometers into the air, blocking out the sun, turning the sky opaque. These storms are driven by temperature differences between the equator and the poles, and they occur most frequently during certain seasons when Mars is closest to the sun and the temperature contrasts are greatest. The storms can last for weeks or months, only gradually settling as the winds calm and the dust falls back to the surface. The dust itself became a defining feature of Mars. It is fine, almost powdery, composed mainly of iron oxide mixed with silicate minerals. This iron oxide gives Mars its reddish color, both in the soil and in the air when the dust is suspended. The dust coats everything, covering rocks, filling craters, obscuring older features beneath layers that can be meters thick in some locations. As the atmosphere continued to thin, the surface pressure dropped. Pressure is simply the weight of the air above, and as air molecules were lost to space, that weight decreased. Today, the average surface pressure on Mars is less than 1% of Earth's atmospheric pressure, roughly equivalent to the pressure at an altitude of 35 kilometers above Earth's surface. At such low pressure, water cannot exist in liquid form except under very specific and temporary conditions. This means that even if ice on Mars were to melt, the water would not remain liquid for long. It would either refreeze immediately if the temperature dropped, or it would evaporate directly into the thin air, skipping the liquid phase entirely through a process called sublimation. This is why liquid water is essentially absent from Mars's surface today, even though ice is abundant. The polar caps grew as the planet cooled. These caps are composed of both water ice and frozen carbon dioxide, also known as dry ice. During winter in each hemisphere, carbon dioxide from the atmosphere freezes out onto the polar cap. adding layers of frost that can be meters thick. During summer, this carbon dioxide sublimates back into the atmosphere, but the water ice beneath remains, permanent features that have persisted for millions of years. The seasonal cycle of carbon dioxide freezing and sublimating causes noticeable changes in atmospheric pressure. During winter, when carbon dioxide freezes at the poles, it is removed from the atmosphere, and the total atmospheric mass decreases. During summer, when the dry ice sublimates, it returns to the atmosphere, and the pressure increases slightly. This cycle repeats every Martian year, a rhythm that has continued for as long as the current climate has existed. Beneath the surface, ice remains trapped in what is called permafrost, soil that is permanently frozen. This permafrost extends from the polar regions down to lower latitudes, reaching depths of several kilometers in some places. The ice mixed into this frozen soil represents a substantial reservoir of water, more than exists in the polar caps, locked away and stable under current conditions. Some of this subsurface ice may occasionally interact with the surface. In certain regions, particularly on steep slopes, dark streaks appear during warm seasons and fade during cold ones. These streaks, called recurring slope lineae, may be caused by briny water with salts dissolved in it that lower its freezing point, allowing it to remain liquid at temperatures below 0 degrees Celsius. The evidence is suggestive but not conclusive, and the exact mechanism remains debated. What is clear is that liquid water, if it exists at all on modern Mars, does so only in trace amounts, under special conditions, and only temporarily. The planet has transitioned fully into a state where water is almost exclusively solid, locked in ice, removed from active circulation, no longer shaping the landscape in significant ways. The volcanic activity that had once replenished the atmosphere also declined. As the interior of Mars cooled, the convection currents that drove volcanism weakened. Fewer eruptions meant fewer gases being released, less carbon dioxide and water vapor being added to the air. The balance shifted decisively toward loss, with little to nothing replacing what was stripped away by the solar wind and other processes. Olympus Mons and the other great volcanoes of Tharsis fell dormant. Their last eruptions may have occurred hundreds of millions of years ago, though the exact timing is difficult to determine. The lava flows that built these mountains are old, cratered by impacts that have accumulated over immense spans of time, indicating that volcanic activity has been absent for a very long period. Without volcanism to release gases, without a magnetic field to protect the atmosphere, without enough gravity to hold on to lighter molecules, Mars was caught in a slow but inexorable decline. The atmosphere that had taken millions of years to build through volcanic outgassing was stripped away over a longer period still, removed by processes that Mars had no mechanism to counter. The loss of atmosphere had cascading effects. With less air to distribute heat, temperature differences between day and night, between equator and poles, became more extreme. The surface, no longer buffered by a thick atmosphere, experienced wild swings in temperature, freezing at night and warming only slightly during the day. These temperature fluctuations contributed to the breakdown of rocks through a process called thermal stress, where repeated heating and cooling causes materials to crack and fragment. The sky changed as well. With a thinner atmosphere, there were fewer particles to scatter sunlight, and the sky took on a different hue. On Earth, the sky is blue because air molecules scatter short wavelength blue light more than other colors. On Mars, with less air and more dust, the sky appears butterscotch or salmon-colored during the day, tinted by the reddish dust suspended in the atmosphere. During sunset, the situation reverses, and the area around the sun takes on a bluish tint, while the rest of the sky remains warm-toned. The thinning atmosphere also meant less protection from cosmic radiation. High-energy particles from distant supernovae and other cosmic events constantly bombard the solar system. Earth's thick atmosphere and magnetic field block most of this radiation, but Mars, with its thin air and no magnetic field, offers little protection. The surface is exposed, and any potential life would need to shelter underground or find other ways to shield itself from this harmful radiation. As the atmosphere became thinner and the surface colder, Mars entered the state that defines it today. The transformation from a wetter, warmer world to a dry, cold one was complete, or nearly so. The processes that drove the change, atmospheric loss, and declining volcanic activity had run their course. What remained was a planet that had used up its capacity for change, at least in dramatic terms, and settled into a long period of relative stability. This stability is not the same as lifelessness or lack of activity. Mars still experiences weather, still has seasons, still undergoes changes. But these changes are slower, more subtle, less transformative than what occurred in the planet's youth. The great rivers have stopped flowing, the lakes have dried, the volcanic mountains have gone quiet, and the atmosphere has thinned to a whisper of what it once was. The loss of the magnetic field, the stripping of the atmosphere by solar wind, the cooling of the interior, and the cessation of volcanism, all combined to drain Mars of its early vitality. These were not sudden catastrophes, but slow processes, playing out over timescales measured in hundreds of millions of years, imperceptible in any single moment, but undeniable in their cumulative effect. Looking at Mars today, it is difficult to imagine the planet as it once was, with rivers carving valleys and lakes filling basins. But the evidence is there, preserved in the geology, visible in the shapes of the land, measurable in the minerals and sediments. Mars changed profoundly and irreversibly from a world where water flowed to one where it is locked in ice, from a place where the air was thick enough to hold liquid water to one where the atmosphere is too thin to support it. This transformation was driven by fundamental physical processes: the cooling of a small planet, the loss of a protective magnetic field, the relentless action of the solar wind. There was no single cause, no single event, but rather a confluence of factors that worked together to strip Mars of its atmosphere and water, to cool its surface, to quiet its geological activity. The planet that emerged from this long decline is the Mars we see today, a world of dust and ice, of thin air and silence, of ancient features preserved in stone. It is a planet that has moved through different states, that has had a history, that once held possibilities now closed. And it stands as a reminder that worlds are not static, that they change over time, that they can transform from one kind of place into something entirely different. Mars settled into this quieter state gradually, without witness, without record except in the rocks themselves. The atmosphere thinned, the water froze, the volcanoes fell silent, and the planet grew cold. What had been a more dynamic world became a still one, a place where time moves slowly, where change is measured over millions of years, where the landscape holds the memory of what was but no longer is. Mars today is a world defined by stillness, by dust, by ice hidden beneath the surface and visible at the poles, by long stretches of time where nothing seems to change. The atmosphere is thin, barely present, exerting less pressure on the surface than Earth's atmosphere does at altitudes where human beings cannot survive without assistance. The air is cold, composed mostly of carbon dioxide with traces of nitrogen and argon, and it offers little protection from the temperature extremes that define the Martian day and night. The surface itself is a mosaic of ancient terrains and more recent features, all covered to varying degrees by a layer of fine dust. This dust is everywhere, coating rocks, filling craters, piling into dunes that shift slowly in the wind. The dust is iron-rich, oxidized over billions of years by chemical reactions with the atmosphere and trace amounts of water vapor, giving it the characteristic red-orange color that makes Mars instantly recognizable. When sunlight strikes this dust-covered landscape, it reflects back in warm tones, rust and ochre and burnt sienna, colors that have come to symbolize Mars itself. The rocks beneath the dust are darker, often gray or black, volcanic basalt that formed during the planet's more active past. But these rocks are rarely visible, hidden under the pervasive dust that has accumulated over immense periods of time. The dust moves. Wind is one of the few active processes still shaping the Martian surface, and it moves dust constantly, picking it up from one location and depositing it in another. The wind speeds on Mars can be high, sometimes exceeding 100 kilometers per hour during storms, though because the air is so thin, the force exerted by even these fast winds is much less than a comparable wind on Earth would generate. Dust devils, small whirlwinds that form when the sun heats the surface unevenly, are common on Mars. They are visible from orbit as dark tracks, where the dust devil has lifted the lighter surface dust and exposed darker material underneath. These dust devils can be tall, reaching several kilometers into the sky, and they move across the landscape, leaving temporary trails that fade as new dust settles. The larger dust storms, the ones that can grow to planetary scale, begin in specific seasons and regions. They typically start in the southern hemisphere during southern spring and summer, when Mars is closest to the sun and the temperature differences between the cold polar regions and the warmer equator are greatest. These temperature differences create pressure gradients, and the air moves from high pressure to low pressure, generating winds. A regional dust storm may begin as a localized event, lifting dust from a particular area. If conditions are right, the storm can grow, spreading to cover larger areas, eventually merging with other storms. The dust lifted into the atmosphere absorbs sunlight, heating the air and creating more wind, which lifts more dust, creating a feedback loop. In some years, this process continues until the storm encircles the entire planet, creating a global dust event that can obscure the surface for months. During a global dust storm, the amount of sunlight reaching the surface decreases significantly. The sky turns opaque, filled with suspended dust particles that block and scatter light. Temperatures at the surface drop slightly because less direct sunlight reaches the ground, but temperatures in the upper atmosphere increase because the dust absorbs solar radiation. This creates a temporary inversion in the normal temperature profile. These global storms do not happen every year. They occur roughly once every 3 to 4 Martian years, though the pattern is not perfectly regular. Some years see only minor regional storms, while other years see the storms grow and spread. The triggers for why some storms become global while others remain regional are not fully understood, though they involve complex interactions between surface properties, atmospheric circulation, and solar heating. When the storms finally subside, the dust settles slowly back to the surface. It does not fall uniformly, but is deposited in patterns determined by wind and topography. Some areas accumulate thick layers of new dust, while other areas are stripped bare, exposing older surfaces. Over time, these processes of deposition and erosion create layered deposits, visible in places where they have been cut through by later erosion or where they are exposed in cliffs and crater walls. The polar regions of Mars are among the most dynamic areas on the planet, at least in terms of seasonal change. The polar caps are made of 2 components: permanent caps of water ice and seasonal caps of frozen carbon dioxide that grow and shrink with the seasons. During winter, in each hemisphere, the temperature drops low enough for carbon dioxide to freeze directly from the atmosphere onto the polar cap, forming layers of dry ice that can extend the cap's reach toward lower latitudes. This seasonal cap can be thick, up to 1 meter or more of frozen carbon dioxide, bright white and highly reflective. As spring arrives and temperatures rise, the dry ice begins to sublimate, turning directly from solid to gas without passing through a liquid phase. The carbon dioxide returns to the atmosphere, and the seasonal cap retreats, eventually disappearing entirely by summer, leaving behind only the permanent water ice cap. The process of sublimation creates unusual features near the poles. As the dry ice warms from below, gas forms beneath the surface layer and builds up pressure until it breaks through, creating jets of carbon dioxide gas that carry dust and sand with them. These jets deposit dark material on the surface of the ice, creating patterns that look like spiders or dendritic systems when viewed from orbit. These features, called arenaiforms, are unique to Mars and are direct evidence of the unusual seasonal processes occurring at the poles. The permanent ice caps, the parts that remain through summer, are composed primarily of water ice. The northern cap is larger and more accessible, sitting relatively flat in the polar basin. It is several kilometers thick in places and contains a significant fraction of Mars's total water inventory. The ice is layered, with distinct bands visible in the exposed edges where the cap has been cut by erosion. These layers record variations in dust deposition and ice accumulation over long periods, creating a climate archive that extends back millions of years. The southern polar cap is smaller and sits atop higher terrain. It also contains water ice, but unlike the north, it retains a layer of frozen carbon dioxide year-round. This permanent dry ice cap is several meters thick and rests on top of the water ice below. The presence of this permanent carbon dioxide ice in the south, but not the north, is related to differences in elevation and seasonal temperature patterns between the two hemispheres. Beneath the polar caps and extending to lower latitudes, substantial amounts of ice are mixed into the soil. This ground ice, or permafrost, exists in a layer that can reach several kilometers deep near the poles and becomes shallower at lower latitudes before disappearing entirely near the equator. The ice is not pure, but is mixed with soil and rock, frozen into a solid mass that is stable under current Martian conditions. This subsurface ice was discovered through various methods. Neutron detectors on orbiting spacecraft can sense hydrogen in the upper meter or so of the surface, and hydrogen is a proxy for water ice. These measurements revealed extensive ice-rich regions at high latitudes in both hemispheres. Later, the Phoenix lander, which touched down in the northern polar region, dug trenches and directly exposed bright white ice just beneath the surface, confirming what the orbital data had suggested. The presence of this subsurface ice means that Mars holds a substantial amount of water, far more than is visible in the polar caps alone. If all this ice were to melt, which it will not under current conditions, it would create a layer of water across the entire planet several meters deep. Or if concentrated, it could form seas in the low-lying northern plains. But the ice is locked away, frozen solid, and will remain so as long as the atmosphere stays thin and the surface stays cold. In some regions, ice is even closer to the surface or exposed directly. Steep slopes in the mid-latitudes sometimes reveal layers of nearly pure ice where erosion has cut into the ground. These ice deposits are thought to be remnants of past climate conditions, when ice could accumulate at lower latitudes than it can today. Perhaps during periods when Mars's axial tilt was different and the climate patterns shifted. Mars's axial tilt, called obliquity, changes over time much more dramatically than Earth's does. Earth's tilt is stabilized by the Moon, which keeps it within a narrow range. Mars has no large moon to provide such stability, and its tilt can vary from near 0 degrees to perhaps 60 degrees or more over timescales of tens of thousands to millions of years. These changes in tilt alter how sunlight is distributed across the planet, affecting where ice can accumulate and where it will sublimate. When the tilt is higher, the poles receive more direct sunlight during summer, and ice there may sublimate and be transported to lower latitudes where it refreezes. When the tilt is lower, the poles are colder and ice accumulates there while lower latitudes become drier. This cyclical variation in obliquity drives long-term climate changes on Mars, redistributing ice and dust, creating layers in the polar deposits, shaping the surface in ways that are slow but significant. The landscape of Mars, shaped by these processes over billions of years, is one of contrasts. There are vast plains, smooth and relatively featureless, where ancient lava flows or sedimentary deposits have created flat expanses that stretch for hundreds of kilometers. There are heavily cratered highlands, ancient terrain scarred by impacts dating back to the solar system's violent youth. There are massive volcanoes, dormant now, but still dominating the landscape with their sheer size. There are deep canyons, valleys carved not by water, but by tectonic forces, by the slow stretching and cracking of the planet's crust. Valles Marineris, the Great Canyon System, stretches across the equator for over 4,000 kilometers, reaching depths of up to 7 kilometers in places. It is not a single canyon, but a complex network of interconnected valleys, some wide and flat-bottomed, others steep-walled and narrow. The canyon formed through a combination of tectonic activity, the stretching of the crust as the Tharsis Bulge rose, and subsequent erosion and collapse. Water may have played a role in some sections, carving channels and depositing sediments, but the primary mechanism was tectonic. The canyon walls expose layers of rock, revealing Mars's geological history in cross-section. These layers include volcanic rocks, sedimentary deposits, and possibly ancient ice. Landslides are common along the steep walls, where gravity pulls loosened material downward, creating debris flows that spread across the canyon floor. These landslides can be enormous, moving billions of cubic meters of rock and soil, reshaping the canyon in sudden events that contrast with the otherwise slow pace of change on Mars. In the northern lowlands, the terrain is smoother, younger, less heavily cratered. This suggests that something resurfaced this region relatively recently in geological terms, though recently still means hundreds of millions to billions of years ago. The mechanism for this resurfacing is debated. It could have been lava flows, widespread volcanic activity that buried the older cratered surface. It could have been sediments deposited by water or ice, filling in the low areas and creating a smoother plain. It could have been a combination of processes working together over long periods. The dichotomy between the heavily cratered southern highlands and the smoother northern lowlands is one of the defining features of Mars's geography. The elevation difference between the two regions is several kilometers on average, creating a distinct boundary that runs roughly along a great circle tilted to the equator. This dichotomy may have been caused by a giant impact early in Mars's history, or by differences in crustal thickness, or by mantle convection patterns. The exact cause remains uncertain, but the result is clear. Mars has two distinct hemispheres with very different geological characteristics. Among all these features, among the dust and ice and ancient craters, Mars serves as a record, a preservation of history that Earth has long since erased. Earth is geologically active, with plate tectonics constantly recycling the crust, with erosion from water and wind wearing down mountains and filling valleys, with life itself altering the surface and atmosphere. The oldest rocks on Earth's surface are less than 4 billion years old, and most are much younger. The record of the planet's early history having been destroyed or buried. Mars, by contrast, has preserved its early history. The lack of plate tectonics means that ancient surfaces remain exposed, untouched by the processes that would subduct them or cover them with new crust. The lack of liquid water means that erosion has slowed to a crawl, unable to wear down features as it does on Earth. The lack of life means that biological processes have not altered the chemistry or structure of the rocks. The result is that Mars holds a record of the early solar system, of conditions that existed 4 billion years ago, of processes that shaped the planets during their formation and early evolution. The heavily cratered surfaces date back to the period of heavy bombardment, when asteroids and comets frequently impacted the inner planets. The ancient valley networks record a time when water flowed, when the climate was different, when Mars was a more Earth-like world. The volcanic plains show the extent of past geological activity, the movement of magma from the interior to the surface, the building of mountains, and the flooding of basins. This preservation makes Mars invaluable for understanding planetary history. Not just Mars's history, but the history of all the rocky planets, including Earth. By studying Mars, we can learn about processes that occurred on Earth but have since been erased. We can see what happens to a planet without plate tectonics, without a strong magnetic field, without a thick atmosphere. We can observe the long-term effects of atmospheric loss, of declining geological activity, of a world that has run out of internal heat. Mars is also a record of climate change on planetary scales, of how a world can transition from one state to another over immense periods of time. The evidence for past water, for a thicker atmosphere, for different surface conditions, all points to a Mars that was once more hospitable, at least by some measures, than it is now. Understanding what caused that transition, what drove the loss of atmosphere and water, helps us understand how planetary climates work, how they can change, what factors make a planet habitable or inhospitable. The planet sits in its orbit, circling the sun, turning on its axis, experiencing its long seasons, its dust storms, its cycles of ice freezing and sublimating. It is not a dead world in the sense of being completely inert, but it is a quiet one, a place where change happens slowly, where the processes that drive transformation operate over timescales that dwarf human experience. It is a world of dust and ice and silence, a world that has moved through more dynamic phases and settled into a state of relative stability. A world that holds within its rocks and ice the story of its own transformation from a wetter, warmer place into the cold, dry planet we observe today. Mars continues to change, even now, even in its cold and quiet state. The changes are subtle, slow, measured over seasons and years rather than hours or days, but they are real. The planet is not frozen in time, not completely still, but moves through cycles that have persisted for millions of years and will continue for millions more. The seasons on Mars are long, each lasting roughly twice as long as seasons on Earth, because a Martian year is nearly twice the length of an Earth year. As the planet orbits the Sun, its axial tilt causes the same seasonal variations that Earth experiences, with one hemisphere tilting toward the Sun while the other tilts away. During summer in the northern hemisphere, that region receives more direct sunlight and temperatures rise, while the southern hemisphere experiences winter and grows colder. 6 months later, the pattern reverses. These seasonal changes drive visible transformations across the surface. The polar caps expand and contract, growing larger in winter as carbon dioxide freezes from the atmosphere, and shrinking in summer as the dry ice sublimates back into gas. This cycle is predictable, reliable, happening the same way year after year with only minor variations. The whitecaps advance toward the equator during winter, bright against the red landscape, then retreat poleward during summer, exposing darker ground beneath. The atmosphere itself changes with the seasons. When carbon dioxide freezes at one pole, it is removed from the air, and the total atmospheric pressure decreases slightly. When it sublimates at the other pole, pressure increases. This seasonal breathing of the atmosphere can change surface pressure by as much as 25% over the course of a year, a variation far larger than anything Earth experiences. The air moves in response to these pressure changes, creating winds that redistribute dust and occasionally trigger storms. Temperature variations between day and night remain extreme. During summer at the equator, afternoon temperatures can rise above freezing, reaching perhaps 20 degrees Celsius in direct sunlight. But at night, temperatures plunge to minus 70 degrees Celsius or colder. This daily swing of nearly 100 degrees is a consequence of the thin atmosphere, which cannot retain heat after the sun sets. The surface radiates warmth into space rapidly once the sun drops below the horizon, and the cold of the Martian night settles quickly. In the polar regions, winter temperatures drop even lower, reaching minus 125 degrees Celsius or below, cold enough that carbon dioxide freezes directly from the air. These are some of the coldest naturally occurring temperatures in the solar system outside the outer planets and their moons. In such cold, any water vapor in the air would freeze instantly, forming ice crystals that fall to the surface as snow. Frost appears on the surface in certain regions and seasons, thin layers of water ice that condense from the small amount of water vapor present in the atmosphere. This frost is most common at high latitudes and in shadowed areas where temperatures remain below freezing throughout the day. It forms overnight and may persist into morning before sublimating as the sun rises and temperatures climb. The frost is delicate, coating rocks and soil in a thin white layer that vanishes as the day progresses. Some slopes in the mid-latitudes show seasonal changes that suggest the possible presence of liquid water, or at least briny solutions that can remain liquid at temperatures below freezing. Dark streaks, narrow and elongated, appear on steep slopes during warm seasons and fade during colder periods. These recurring slope lineae, as they are called, may be caused by water containing dissolved salts, which lower the freezing point and allow the solution to flow briefly before refreezing or evaporating. The evidence for these flows is not conclusive. The streaks could also be caused by dry processes, perhaps flowing sand or dust triggered by temperature changes. But the possibility of even small amounts of seasonal liquid water has significant implications, both for understanding Mars's current water cycle and for considering whether any microbial life could exist in such environments. If liquid water does appear, it does so only in tiny quantities, in isolated locations, and only temporarily. Erosion continues on Mars, though at rates far slower than on Earth. Without liquid water to carve valleys or rivers to transport sediment, the primary erosive force is wind. Wind picks up dust and fine sand, carrying it across the surface. abrading rocks through a process similar to sand blasting. Over millions of years, this wind erosion can wear down features, smooth, rough surfaces, and create ventifacts, rocks carved into unusual shapes by persistent wind-driven particles. Larger rocks, boulders that have fallen from cliffs or been ejected by impacts, weather slowly through thermal stress. The repeated heating and cooling of each day causes the rock to expand and contract slightly, and over long periods, this can cause cracks to form and propagate. Eventually, the rock may split, breaking into smaller pieces that are more easily moved by wind or affected by other processes. Impacts still occur, though much less frequently than during the solar system's early history. Small meteorites strike the surface occasionally, creating fresh craters that appear as bright spots before dust gradually covers them and they blend into the surrounding terrain. Larger impacts are rare, but do happen, and each one adds to the long record of bombardment that has shaped Mars's surface over billions of years. Avalanches and landslides happen on steep slopes, particularly in areas where ice is present near the surface. When ice sublimates or when temperature changes weaken the stability of a slope, material can suddenly give way, cascading downward and leaving behind fresh scars visible from orbit. These mass movements are among the more dramatic events on modern Mars, sudden releases of material that reshape local topography in moments, contrasting with the otherwise slow pace of surface change. The geological processes that once drove major transformations on Mars, volcanism and tectonics, have slowed to near stillness. There is no evidence of recent volcanic eruptions, no lava flows that appear fresh or uncratered. The volcanoes stand silent, their slopes aged and dust-covered, their calderas empty and cold. If magma still exists deep beneath the surface, it no longer has enough heat or pressure to break through and reach the surface. Similarly, there are no active tectonic plates, no continents drifting or colliding, no mountain ranges being thrust upward by compressional forces. The crust has cooled and solidified, becoming rigid and stable. Any tectonic activity that might still occur would be minor, perhaps slight adjustments as the planet continues to cool and contract, but nothing that would reshape the surface in noticeable ways. Marsquakes, seismic events detected by instruments placed on the surface, do occur. The InSight lander, which operated on Mars from late 2018 until late 2022, recorded thousands of Marsquakes during its mission. Most were small, barely perceptible tremors caused by the cooling and cracking of the crust or by meteorite impacts. A few were larger, deeper events that may have originated from remaining stresses in the planet's interior. These quakes tell us that Mars is not completely geologically dead, but the level of activity is far below what Earth experiences. The planet's interior remains largely mysterious. We know from the way Mars responds to the Sun's gravitational pull that it has a core, likely composed of iron and nickel, and that this core may be partially liquid despite the overall cooling of the planet. The mantle above the core is solid rock, no longer convecting vigorously as it once did. The crust varies in thickness, thicker beneath the southern highlands and thinner beneath the northern plains. a difference that contributes to the planet's geological dichotomy. Mars rotates at nearly the same rate as Earth, completing one turn in just over 24 hours. This rotation creates a Coriolis effect that influences atmospheric circulation, causing winds to curve rather than flow directly from high pressure to low pressure. This effect contributes to the formation of weather patterns, including the spiral structure sometimes visible in large dust storms. The planet's two small moons, Phobos and Deimos, orbit close to Mars, closer than any other moons in the solar system relative to their planet. Phobos, the larger of the two, orbits so close that it completes 3 full orbits in a single Martian day. It is gradually spiraling inward, drawn closer by tidal forces, and will eventually either crash into Mars or be torn apart by gravity to form a ring system. This will not happen for millions of years, but it is an inevitable consequence of the moon's proximity. Deimos orbits farther out and is slowly moving away from Mars, though much more gradually than Phobos is approaching. Both moons are small, irregularly shaped, heavily cratered, and likely captured asteroids rather than moons that formed alongside Mars. They are dark, covered in dust and regolith, and they cast shadows on Mars's surface during their transits across the Sun. Brief eclipses that darken small patches of ground for a few minutes. As Mars moves through its slow cycles of seasonal change, of ice advancing and retreating, of dust storms rising and settling, humanity has begun to turn its attention toward this distant neighbor. For centuries, Mars was a point of light in the night sky, a wanderer among the stars, mysterious and unreachable. Then came telescopes, which revealed surface features, polar caps, changes that suggested seasons and perhaps even life. The first spacecraft to visit Mars arrived in the 1960s, simple probes that flew past the planet and returned a handful of images. These early missions revealed a cratered, moon-like surface that dashed hopes of finding a vibrant, inhabited world. But they also sparked curiosity, a desire to know more, to look closer, to understand what Mars truly was. More missions followed, orbiters that mapped the surface in increasing detail, landers that touched down and analyzed the soil, rovers that rolled across the landscape and drilled into rocks. Each mission added to the growing body of knowledge, revealing Mars not as a simple, dead world, but as a complex planet with a rich history, with evidence of past water, with features that told stories of volcanic eruptions and flowing rivers and changing climates. The discovery of ancient river valleys and lake beds transformed our understanding. Mars had once been different, more Earth-like in some ways, and the question arose, could life have existed during that wetter, warmer period? The search for signs of past life became a driving goal of Mars exploration, motivating missions designed to look for organic molecules, for chemical signatures, for anything that might indicate biology once took hold. Rovers like Spirit, Opportunity, and Curiosity explored different regions, each chosen for its potential to preserve evidence of past water and habitable conditions. They found minerals that form in water, layered sediments deposited in ancient lakes, chemical environments that could have supported microbial life. They did not find life itself, But they found that Mars once had the ingredients, the right conditions, at least for a time. The Perseverance rover, which arrived in 2021, continued this search in Jezero Crater, the site of an ancient river delta where water once flowed and deposited sediments. The rover is collecting samples, carefully selecting rocks that might contain biosignatures, sealing them in tubes that will eventually be returned to Earth for detailed analysis. This sample return mission, planned for the coming years, represents a major step in the exploration of Mars, bringing pieces of the planet back for study in laboratories far more sophisticated than anything that can be sent to Mars. Alongside the scientific exploration, a different kind of interest in Mars has grown, a vision of human exploration and eventual settlement. The idea of sending people to Mars, once confined to science fiction, has become a serious topic of discussion among space agencies and private companies. The challenges are immense. The journey takes months. The radiation exposure is significant. The lack of breathable air and liquid water makes survival dependent on technology, and the distance makes rescue or resupply missions difficult. Yet the interest persists, driven by a combination of scientific curiosity, the desire to extend human presence beyond Earth, and the long-term goal of making humanity a multi-planetary species. Mars, being the most accessible planet beyond Earth, with a solid surface and resources that could potentially be used for life support, has become the focus of these ambitions. Plans for human missions involve sending astronauts to live on Mars for extended periods, perhaps a year or more, conducting research, testing technologies for living off the land, and preparing for potential future settlements. These missions would require habitats to protect against radiation and provide breathable air, systems to extract water from the soil or atmosphere, and methods to produce fuel for the return journey using Martian resources. Some envision even more ambitious goals: terraforming Mars, transforming it over centuries or millennia into a more Earth-like world with a thicker atmosphere, warmer temperatures, and perhaps even liquid water on the surface. This would require adding massive amounts of greenhouse gases to trap heat, perhaps by releasing carbon dioxide locked in the polar caps or in the soil, or by importing volatiles from elsewhere in the solar system. The technical and ethical challenges of such an undertaking are enormous, and whether it is even possible remains uncertain. For now, Mars remains a frontier, explored by robots but untouched by human hands. The rovers roll across ancient lakebeds. The orbiters map the surface in exquisite detail. The landers measure Marsquakes and weather patterns, all sending data back across the vast distance to Earth, where scientists piece together the story of a world that was once wetter and warmer, but has settled into cold silence. And Mars itself continues its slow journey through space, orbiting the Sun in its elliptical path, turning beneath the distant stars, its seasons cycling, its ice advancing and retreating, its dust moving in the wind. It is a planet that has changed profoundly over billions of years, that holds within its rocks the memory of flowing water and volcanic fire, that serves as a record of planetary evolution and a reminder of how worlds can transform. It is a companion to Earth, moving alongside our own planet through the solar system, close enough to reach but far enough to remain other, familiar in some ways but alien in others. It has captured human imagination for centuries and continues to do so. A destination for our machines, a subject of our curiosity, a possible future for our descendants. For now, Mars rests in its quiet state, patient and still, while dust settles on ancient valleys and ice lies frozen beneath the surface, while the thin atmosphere whispers across empty plains and the cold night descends after each brief day. It is a world apart, a red neighbor in the darkness, holding its secrets, preserving its history, waiting beneath a butterscotch sky for whatever changes the long future might bring. The story of Mars is not finished. It continues to unfold in subtle ways, through seasonal cycles and slow erosion, through the gradual evolution of its climate over millions of years, through the axial wobbles that redistribute ice and dust. And now, perhaps, the story includes a new chapter, one written by visitors from Earth, by machines first, and possibly by people later, exploring this quiet world, seeking to understand its past, and dreaming of what its future might hold. Mars remains itself, a planet of dust and ice and silence, moving through space beside Earth, separate but connected, different but not entirely foreign, a world that once held water and may someday again echo with the sounds of exploration, discovery, and perhaps even life returned to its surface after billions of years of absence. For now, it turns quietly in its orbit, patient, still, a red point of light in Earth's sky, a rust-colored world beneath a distant sun, resting beside its neighbor, moving together through the vast emptiness of space and time.